Hello everyone, my name's Logan and welcome back to the lecture hall. For today's video, we are covering inverses and logs. So if we have a function, we know a function takes elements in one set and maps it to another. Like so, we could take all the elements in A and map them to B, and that would be a function, right? Well, what would the inverse be? The inverse, well, it's kind of like the opposite, and it's the map the opposite direction. So our function takes elements from A to elements in B, while our inverse is going to take elements in B and put them back into elements in A. So we can kind of see that. We map all of ours to B, from A to B, and then our inverse would map all of our points from B to A. What do we notice about these sets? Well, we only have one input for every output and one output for every input. That is very important. Inverses are required to be one-to-one and onto, which we are getting into right now. So we have our definition of one-to-one, and it states if for every f of x1 not equal to f of x2, then x1 does not equal x2. And essentially what this is saying is you cannot have multiple x values corresponding to the same y value. And now we can get into the definition of the inverse, and it says let f be a one-to-one function with domain A in range B. Then f inverse has domain B and range A such that f inverse of y is equal to x if and only if, that's what this double biconditional arrow means, f of x equals y. And then this upside down A means for all y in B, which means for every element y in the domain B. So, brief overview, for inverses, the domain of our function becomes the range of our inverse, and the range of our function becomes the domain of our inverse. All right, now we're going to just blast through our laws of logs. So what are logs? Well, a log base b of y is equal to x if and only if b to the x equals y. So we're like, this is an inverse video. We're talking about logs and we see an exponential. So we can deduce that this is in fact an inverse of our exponentials. So logs are inverses of exponentials, and we have our laws of logs, and they follow similarly to our exponentials. Log base b of x times y is actually equal to the log base b of x plus the log base b of y. Log base b of x divided by y is log base b of x minus log base b of y. We then have log base b of x to the a power. That is actually equal to a times log base b of x. Then we have our change of base formula, and this is very helpful. I actually used it in my senior year research. Log base a of b, well, that's actually equal to log base x of b divided by log base x of a. All you have to make sure is that these two bases are the same base. So for this final little piece, we're covering inverse trig functions. So do not confuse these with our reciprocal trig functions. Sine inverse of x is not equal to cosecant of x. Cosecant of x is 1 over sine x. So we have sine inverse of y equals x if and only if sine of x equals y and y has been restricted from negative pi over 2 to positive pi over 2. And the only reason we have to do that is so that our function is still one-to-one and it will still be a function and invertible. We have cosine inverse of y equals x if and only if cosine of x equals y, and our domain of y is restricted from 0 to pi. And then tan inverse of x, or tan inverse of y equals x if and only if tan of x equals y, and our domain for y has been restricted to negative pi over 2 to pi over 2, just like it was for sine. And then our final note for inverses states that f of f inverse of x equals f inverse of f of x, which equals x. We are assuming that this f is invertible. And so what does this mean? Well, essentially, we're just going to get, these just cancel each other out and just give us x. So sine inverse of sine of x, x. e to ln of x, well, that just equals x. And so we just need to remember this when working with inverses. This is probably our most important piece. So that's everything I wanted to cover in today's video. I believe this was the last of the not calculus. We will be, I'm going to keep chugging along with these videos. I'm actually having a really good time, and I'm I don't know, I'm feeling myself right now. So as always, my name's Logan. Thanks for watching. Have a great day.